Okay, let's get started. Last week, we learned some program flow control. First of all, we learned the jumps instruction. And there are two different jumps, unconditional jump and conditional jump. And also there are another type of jump called the subroutines. And remember that we mentioned the unconditional jump, right? And there are three different instructions for unconditional jump. First one is the short jump, S jump. The reason that we call this one as a short jump is because that the address, the following address is 8-bit. And this is particularly, we call this a relative address because this is going to be the jump compared to your current address. So you are in a certain address, and short jump basically tells you that you're going to either jump forward up to 127 bytes, address bytes, or jump backward with a minus 128. So compared to your current address, you can jump forward with a limited bytes address or jump backward. But the total address for the jumping is 256. Okay? So we use 8 bits for relative address. That's a short jump. There are another type called the long jump. Long jump, you have a full address. Since we have the address space of 16 bits, right? 64K. 64K, as you know, is a 16-bit address. So therefore, you can just specify where to jump. Okay? Within the 64K, you can specify, I'd like to jump there. Okay? And then put that address, destination address here as a 16-bit. So that's going to be a long jump. This is not relative address. This is the absolute address. Another type of instruction in unconditional jump is A jump, absolute jump. Right? In this case, you use 11 bits of address space. And 11 bits looks like this. We have 8-bit of operand, OP code with the another 8-bit of instruction, the operand. And the first 3 bits of the OP code is combined with the second byte. So therefore, you make 11 bits. That's going to be your absolute address. And in this case, it's 11 bits. Since we have 8 bits for relative address for short jump, the total range for jumping is only 256 bytes. Whereas in long jump, you have 16-bit of address. So therefore, you can have 64K of address space. And you can jump anywhere you want. In A jump, you have 11-bit address. So therefore, the range of jumping is 2K. Okay, 2 kilobytes. And you see that this map basically shows you the range. So as you can see here, basically long jump covers the whole range. The whole range, you can jump anywhere using the absolute address. And A jump uses a 2K. So within the 2K here, you make 8 different pages. Each page is 256 bytes. Since we have 8 different pages, the total is 2K, okay, 2 kilobytes. So you can jump within the 2K. That's A jump. Whereas a short jump, you can jump only within the 256 bytes, only the near location. There are conditional jump, which is more popular when you program it. We can look at the examples. For example, JZ means that we are going to jump if the accumulator is 0, right? Not 0. And JC means C means carry. So when you have a carry equal to 1, then we jump. So for each of these instructions, the operand is relative address, same as our short jump, right? So which basically means that this address is only 8-bit, and you can jump forward by maximum 127 or jump backward by minus 128, right? So the range of jumping, again, is only 256 bytes. 127 forward, minus 127 backward, okay? For all these things. Not carry. JB means you have a bit address as the first operand and relative address as the second operand. So you have two different operands for this instruction. if this particular bit is 1, then you jump. And if that bit is not 1, then you jump. Right? And J, B, C, B means bit again. And if this bit equal to 1, then you jump and clear the bit. Okay, this bit equal to 1, right? So you jump it and you clear. So make it 0. Right? So combine JB with clear together. Okay? Just combine the two different instructions and make it one instruction. That's JBC. C means compare. So in order to compare, basically you need to have two different operands. A, in this case, and with the internal RAM address. So you're comparing these two, right? If compare these two and those are not equal, then you jump. Where to jump? You jump to relative address. Okay? Basically same thing. DJ and Z. D means decrement. So first of all, in this case, you are going to decrement the value, the first operand. In this case, it's like R0 or R1. So you first decrement it, and then jump if this value is not 0. Okay? So you already looked at this one in the midterm, so I'm sure that you understand what it is. Okay. Also, we learned another type of jump or the flow control instructions called the call and return. Right? The difference between the call and return and the previous jump is that previous jump, right, unconditional jump or conditional jump, what happens is you jump and that's it. Okay? Sometimes you jump when the condition is met, but once you jump it, then that's it. You are not going to return, right? There's no guarantee. However, in this case, the call instruction and return together, what happens is you jump, and whenever you see return, then you're going to come back. Okay? You're going to come back where you left off. Okay? That's a difference. But in order to come back, right? What happens is before you jump, you have to push the program counter value on the stack. So therefore, whenever you finish your subroutine, you will see return, and this return instruction basically pops the previous program counter from the stack, okay, and restore this program counter value. Therefore, you jump back to your original location. That's the only difference. So using stack to push and pop, okay, your previous address. So in call instruction, there are also the A call, L call, same as the A jump and long jump. Okay, this was the example that we looked at last time. Actually, this midterm, we didn't have any questions about the stack, right? Because we only have 90 minutes for the exam, so I think we didn't have time to do this, but maybe in final exam or possibly in a quiz sometime, maybe we will not test this. So I want you to look at this one and understand this stack, okay, very well. Okay, you need to understand this one very clearly, how to work. Okay, let me repeat one thing. Let's look at this one, right? Let's put this 76 into the stack pointer. Then you have the values here, 76. And remember that 76 is the bottom of your stack right now. Right? So let's say this is a box called the stack. And maybe there's some books in the box, right? This last one, which is the bottom, that's the stack pointer. Okay? The book, the last book, you push it into the stack. That's the stack pointer. So now, later, I want to call the delay function. So therefore, when I execute this instruction, I'm going to jump to delay subroutine. But before you jump, right, what you want to do is you want to store the program counter value to the stack. So before you jump, let's say I'm trying to jump, so I'm executing this one, actually this one, right? So what value do you have in the program counter? When you execute this one, right? The value in the program counter would be? What value do you have in here? When you execute this one?
0, 1, 0.
You have this value, right? 0108. That's in the program counter. Okay? Program counter has the value 0108. Now, we want to execute this call delay, so therefore I want to jump. But before jump, I want to copy this program counter value into stack. Okay? But before you do that, right, what do you need to do? Right now, the stack pointer is pointing here. Right? In order to copy this value to here, what do you need to do? First of all, you want to increment the stack pointer. Because right now the stack pointer is pointing the last value in here. Okay? So therefore, first one is you increment the stack pointer. So now my new stack pointer is right here. It's incremented. And then you copy 2 bytes here, here. Okay? Maybe 01 and 08. This maybe go into 010A or maybe 0801. Okay? Depend on Indianness. But anyway, you copy these 2 bytes into stack. And then now my new stack pointer goes to here. Because this is the last one in my stack. That's the bottom of my stack. Right? So therefore, eventually, my stack pointer, original stack pointer was here in SP, right? Was right here. Okay? But I push the 2 bytes into the stack. So therefore, eventually, my stack pointer has been increased by 2. Eventually, right? Earlier, stack pointer was here, but now my stack pointer is here. Okay? But remember that when you push the value into stack, you have to do +1 first. You have to do +1 first. Let's say that's what we have here, right? So we have the 70 value move into the stack pointer, right? And let's say we are trying to execute this line. Okay, now the question. Okay, so we have the program counter value 010A, and previous the initial value of stack pointer was 76. Now let's say I'm trying to execute this line. So when I execute this line and I jump, let's say I jump to here. Okay, when I jump to here, and let's say I stop it here. Let's say I put the breakpoint here. So when you run it, then I jump already and I stopped here. Okay, when you stop the program right here, now then what's going to be the value of all of this? Let's say I put the breakpoint right here. So I stopped here. First of all, what value do you have in program counter? When you stop here, right, then the value here is 0302. Okay? Because that's the next instruction. Right? What value do you have in stack pointer? You have the value? 78. And what value do you have here? Here, what value do you have? Huh? We don't know. We don't know. Okay? And what value do you have? It's like a 0108. Or it could be 0801, but it's like this, right? Remember, it's not like if you write this way, that's wrong. That's what I'm saying, right? First, you have to increment SP. You have to increment the stack pointer first, and then you store the value. Okay, remember this. Okay. Okay, so that's a very important one. Okay, let's talk about today's topic. Today, we are going to learn interrupts. Interrupt. What is interrupt? Simply speaking, this is interrupt. Let's say I'm reading a book at home. Okay? At home, I'm reading a book. And suddenly, my telephone rings. That's interrupt, right? That's interrupt. So what do you need to do? What you need to do is that you stop reading and go and get the phone, right? Go to get the phone. And then maybe it's your friend. So you talk to your friend, maybe 10 minutes or so. And then you hang up and come back and you want to read it again, right? You want to continue to read. Now what's the problem? I forgot. I was reading here, but after I hang up the phone, I come back and I forgot where I was reading. So that we have the same problem here as the call and return. Okay, the previous call and return, you are basically, whenever you see a call instruction, you jump to subroutine and you continue executing the subroutine, and whenever you have return, then you come back where you left off, right? You come back and continue. Similar in some way, because you were reading a book and at a certain point you have to stop and go there and pick up the phone and talk to your friend, come back here, and you want to continue from where you left off. So what do you need to do? You have to do the same thing. You have to push before you jump. Before you go and get the phone, you have to mark it. Okay, I have read up to here, up to this line. Okay, you mark it and go there and talk to your phone, talk to your friend, whatever you want, and come back here and find the mark and continue read from that mark and onward. Okay, so what that means is you have to push your program counter to the stack, same way. And then when you finish your interrupt routine, interrupt subroutine, this is called the interrupt service routine, ISR, interrupt service routine. Whenever you finish your interrupt service routine, you have to come back. And how do you come back? You pop the stack pointer from the stack, pop the program counter from the stack. Okay? Same way in the call and return. Then you you recover the program counter, then you come back where you left off and continue. Okay? So some sense, this one, interrupt, is pretty much the same as call and return. Okay? You store the program counter to the stack before you jump, and whenever you want to come back, you basically restore the program counter from the stack. Same way. However, this one is very different. What is different? Compare the interrupts with the call and return. What is the difference?
There is no instruction call.
Yeah, exactly. In the call and return, what happened is that, look at the earlier case, we know when we jump, right? You see, whenever you have some instruction, right? We have a call instruction, so this is where you jump. This is when you jump. And we also know that whenever we finish the subroutine, we are going to jump back here. We know that. Okay? Because it is call instruction, we're going to jump right here. However, in interrupt, there's no instruction call, or there's nothing like that. So for example, come back to our example. I was reading a book. I have no idea when my friend is calling me. I have no idea. Maybe he's calling me now, or maybe in 10 minutes, maybe tomorrow, I don't know, right? So the interrupt basically comes at random time. It comes unexpectedly, right? That's the difference. Look at this program. In this assembly program, there's no sign of jumping. There's no instruction for jumping, right? It is just simply like a move and multiplication and just a normal instruction. However, when interrupt comes, like a telephone rings, then suddenly it jumps. And then maybe you talk to your friend, something like this, right? And whenever you finish your interrupt service routine, then at the end of your subroutine, interrupt service routine, you have a instruction called return I. I means interrupt, okay? Because this is also a subroutine, interrupt service routine. So at the end of the interrupt service routine, you have a return I. Whenever you have a return I, then you're gonna come back right here because you basically jumped when you are here, so therefore you jump back right here. So that's the difference. You don't know when you jump in interrupt. That's the only difference. In 8051, in our microprocessor, we have 5 different interrupts. Timer 0, 1, 2 timer interrupts, external interrupt 0 and 1, 2 external interrupts, and 1 serial port interrupt. There are 5 different interrupts. This is an 8-bit microprocessor, so we have only 5. But if you look at the 32-bit microprocessor, sometimes you see like 20, 30, or even 60 different interrupts. So there are so many different interrupts. For example, right? Let's come back to our example. Let's say you're reading a book again, and one possible interrupt source is telephone. And maybe another type of interrupt would be like a doorbell. Someone is coming and ding dong, like pushing the doorbell. That's another interrupt. So now, this interrupt is definitely different. These two are completely different interrupts. Suppose that you're reading a book, right? And someone is knocking the door. And at the same time, let's say your friend is calling me. So telephone rings and also doorbell rings. Which one do you want to get first? Do you want to pick up the phone first, or do you want to go and open the door and see who is there? Which one is more important? That's the concept of interrupt priority. Okay? In our microprocessor, we have 5 different interrupts. Timer interrupts, 2, external interrupts, 2 of them, and serial port interrupt. But each of them may have a different priority. As I said, right, in our example, let's say your telephone is very important. You are waiting. Okay, you're waiting telephone. Maybe your friend said that, okay, I'm going to call you with a very important thing, something like this, right? Then you are waiting. In that case, of course, you wanna ignore the doorbell. Okay, I don't know, maybe some random guy, okay, knocking the door. So I don't care. I'm going to pick up the phone. But generally, how do you do it? Let's say you don't know who is there in your door and who is calling you. So let's say you don't know anything about those things. Then which one do you want to pick up? Maybe you go there and pick up the telephone and check who it is, right? And if that is your friend, then maybe you can tell him that, okay, wait for a minute. Okay, and then go there and open the door and check who he is, right? So maybe pick up this first and let him wait, and then go there and check the doorbell. Check the door, who he is. That's also possible, right? What do you want to do? That depends on the priority. So this priority is not fixed. If you want to make doorbell as a high priority, then you can set it that way. Or if you want to have, okay, I think my telephone is more important, then you can put a high priority for telephone. Okay, this is up to you. You are gonna set. In 8051 again, let's say we have timer interrupt and external interrupt. And if you want to have a higher interrupt for external source, then you can set it that way. Okay? But if you want to make a timer as more important, then you can make timer interrupt as a higher priority. Okay, you are going to set the priority for each of them. we also have to understand this one. This is also another very important thing. The condition of an interrupt. Okay, let's come back to our illustration. You're reading a book, and let's say yesterday my friend tell me that, okay, I'm gonna call you tomorrow. So basically I'm expecting, right? I'm waiting his call today. So in that case, you have to check first. Check something. What do you need to check? First thing to check is that maybe you can go there and check your telephone. Maybe your telephone does not work, maybe, right? And check the plug. Maybe your telephone plug, the telephone line, maybe it's disconnected. Who knows, right? You have to check if telephone is working fine. And also, and another thing that you want to check is that maybe if that is a very important call, then maybe you want to check. Maybe like using your telephone, your cell phone, maybe you want to call your home and check if the telephone is ringing. Maybe your telephone is like in a mute mode, maybe. In that case, telephone may not ring, right? In that case, even though your friend is calling you, you may not be hearing. So you need to check those things. Like a doorbell, for example, right? Let's say I'm waiting a very important guest to come. In that case, what do you want to do? Maybe you want to go out there and check if the doorbell is working properly. And also, maybe you want to go there and check the electricity. Maybe if the electricity is out, maybe if we have outage, electricity outage, then maybe doorbell is not ringing. Okay? Some of those things. Same way here, if the interrupt event is trying to occur, if the interrupt comes only when interrupt flag for that particular interrupt is enabled and interrupts itself is enabled. Okay, what that means here is that this one. This is a one register called interrupt enable, IE. This is another register. So far, we learned the register called the program status word. We have some other registers, right? R0, R1, accumulator. There are many different registers. Those R0, R1, A, those things are general purpose registers, right? You can store some value into those registers, and you use those registers to do addition and any of your calculation, whatever you want. However, this particular register is for interrupt. Okay? Let's see what it is. The first one, EA. What is EA? This is a global interrupt enable. What that means is, this is like your, think about your home. This is something like your electric power switch of your home. If this one is 0, that means your whole power, electric power in your home is out. Okay? Like you turn off your electricity of your home, the entire home. In that case, right, think about it. Let's say you turn off your switch, electric switch of your home. In that case, nothing works, right? Telephone doesn't work, doorbell doesn't work, nothing works. Same here. If this is 0, then all of the interrupt is off. It does not work. And if this is 1, right, then it's like same as you turn on your electrical switch in your home. So therefore, now each of the interrupt may work. May work. Okay? So this is a global interrupt enable. And now that we have 6 different bits, but this one, ET2, I think this is not used for our 8051. This is only for 8052. So forget this one. So now we have 5 different bits from bit 4, 3, 2, 1, 0. So each of these bits is for different interrupt source. This one is external interrupt 0. This is timer interrupt 0. External, X means external interrupt 1, timer 1, and this is a serial port. We have 5 different interrupt sources. So for each of the bit, is enable bit for each different source. So here's the case. Let's say I want to make this one as 1, right? Meaning that I'm enabling the all interrupt. This is 1. And let's say I want to make all 0. 0, 0, 0, 0, 0. In that case, something like this. You turn on your electric switch of your whole entire house, right? But your telephone is not plugged in. So therefore, telephone doesn't ring. Your home has electricity, but your telephone is plugged out. Same as that. When you have 1, let's say make it this 1, okay? Only then what that means is you plug in your telephone. So your telephone is now working. So in order for each interrupt to work, you have to make sure that this is 1. Your home has to have electricity. And also, this one has to be 1. Both one has to be 1. This one is a 1, and this one is 1 for timer 0. And if you want to have an external interrupt 1, then of course this one has to be 1, and this one also has to be 1. You can enable 2 different interrupts, timer 0 and external 1 at the same time. Then this is 1, then 1, 1. Okay? That is the minimum condition for interrupt. Okay? What that means is this one is you turn on your electricity of your home, and you now plug in your telephone to the power. So therefore now your telephone is working. So we have a minimum requirement of these things. And in addition to that, in order for telephone interrupt, what do you need? We have additional thing. We need to have electricity of your home, and we also have to make sure that your telephone is plugged in to the power. And there's one more thing. Your friend has to call you, right? Telephone is plugged in, but telephone does not work, does not ring, right? It works, but it does not ring. Only when your friend is calling you, then it rings, right? So there are third condition, meaning that your actual interrupt event should occur. That's what this means. Interrupt event occurs, and interrupt flag for the event is enabled, which means that you know that there are 5 different interrupts, right? 5 different bits. That's what they mean. Interrupt flag for that particular event should be enabled, and also the global interrupt bit is enabled. So we have to have 3 different conditions. Only then you have interrupt. Okay? Only then. So when you have this one, this condition, this condition, this condition, all of them are on, then now we have interrupt. So now let's see what happened when you have interrupt. When interrupt comes, then first of all, your current program counter is pushed to the stack. Same as call instructions. Okay? Because we need to come back later, right? So your current PC program counter is pushed to the stack, and jump to interrupt vector first, right? And find out where to jump. I'll tell you this one in the next slide. And then whenever you see the return I instructions at the end of your interrupt service routine, then you're gonna pop the program counter from the stack, okay, and restore the program counter, and then you come back, and main program will resume. So now then, come back here. Compared to the call instructions, right? As I said, in this interrupt service routine, you can jump anytime. Maybe your friend is calling you at here, maybe at this time. Maybe your friend is calling you some other time, right? Interrupt can happen anytime. And whenever you have an interrupt, you jump. Now then, we have a problem compared to previous one, right? This is a call instruction. In this call instruction, whenever we have a call, we jump. And not only that, we know where to jump, because it says the call, delay. And we are going to jump to this one, delay. And delay is right here, right? So we know that we are going to jump to delay. However, in this case, right, there's no such thing. Interrupt comes anytime, but I don't know where to jump. It doesn't say anything, right? So where to jump? interrupt can happen anytime, but I don't know where to jump. Here, I mean, where is this one? We need to jump to interrupt service routine, but I don't know where is this. Okay? So that's a problem. So therefore, in interrupt service routine, we have interrupt vector. Okay? We have interrupt vector. And this is the destination of your jump. Whenever you have interrupt, you're going to jump to this particular address. So if your interrupt, for example, is external interrupt 0, then you're going to jump to here. And if your interrupt source is timer 0, then you're going to jump to this one. So where to jump, it's already programmed in the hardware. Okay, in the hardware, whenever you have, depending on which interrupt you have, you need to jump to this known location. This is already decided. Okay, this is already programmed in the hardware. So this is where you jump. Now what's the problem? Now we know where to jump. This is where to jump, actually. So come back to program. Let's say we enable the interrupt by setting this bit 1. And let's say I want to have timer 0 interrupt. In that case, you want to make this one as 1, this bit 1, and this bit to 1, right? If you make 1, 1, now we are ready to get a timer 0 interrupt. And later, you need to also program the other registers in order to make the timer interrupt occurs. We need to make the timer event occurs. Okay, that's another thing. We're going to talk about that in a minute. But let's say you have to enable this one, and also you have to program another registers to make a timer happens. And once you do that, when timer occurs, event occurs, then you're going to get the interrupt. And whenever the interrupt happens, then now we know that we're going to jump to this place. Because this is where you're going to jump to when you have interrupt. Now we have a problem. The problem is that, look at this address, 000B, right? And we know that this particular address, 0013, is also reserved for interrupt vector for another interrupt source. This particular address is for external interrupt 1. So what happened is, we don't have enough space between these two. Okay, whenever we jump to this interrupt service routine, we want to do something inside the interrupt service routine, right? For example, when you get a call from your friend, then you want to go there and pick up your phone and you want to talk to your friend, maybe 10 minutes, right? Right? You don't want to go there and pick up the phone and say hello and hang up, right? You don't want to do that. You want to have your program. But these addresses are already reserved for some other thing. So what do you need to do then? So this is the problem. There are only 8 bytes between these two. Between these two. That's the problem. So therefore, this is what is happening. Generally speaking, this is what's happening. First of all, you need to understand this one. You know, when you power up your microprocessor, right? Your microprocessor always starts from 0000 address. This is the first address you start when you boot up your microprocessor. And this particular address is called, this is also another type of vector, right? And whenever you come here, you always see like long jump start. Your program is not here. Okay? Your program is not going to be starting from 0, 01, 02. Your program is not here. Your program will be always in some other location. That's why we always use like org 100H, something like this, right? We use a directive for doing that. So your program is always some other place here, but microprocessor will always start from 0000. So how does it work? So therefore, when you write the program, at the 0000H address, you have to make sure that you have a long jump start. You always want to add this one. So therefore, when the microprocessor boots up, then it comes here because this is the first address to start. And particularly this one actually is this instruction was a long jump start. So therefore, when the microprocessor starts from here, then immediately jump to start. This is a start. Right here, start, right? 100H. So whenever the microprocessor starts from here, then you jump and then continue. And this is where your program is, right? Okay? So therefore, you have a long jump start right here. Interrupt service routine is almost the same thing. So let's understand what happened. This is what happened at the very first place in the microprocessor. Okay? Whenever you boot up microprocessor, it starts from 000H, and the instruction in here actually was a long jump start. So therefore, you do long jump. And you start from here. And that's actually your program. And let's say while you are running your program, like number 2, let's say suddenly external interrupt 1 occurs at this time. This is some random time. We don't know when we get the interrupt. But just as an example, let's say we have external interrupt 1 at this time. In that case, what do you need to do? Since you have interrupt source coming in, what you need to do is you need to jump to interrupt service routine. So where is the interrupt service routine? In this case, it's here. As I said earlier, this is called the interrupt service vector. Okay? So you need to jump here first. That's the known location, right? That's a reserved destination of your interrupt source. So for this, in this case, this is actually interrupt service, external interrupt source 1. So come back here. External interrupt source 1, I said that the 0013 is your destination. Whenever you have interrupt, you have to jump to here first. So let's see. And while you are running your program, suddenly the interrupt service 1, external interrupt 1 occurs at this time. Then you need to find it, where is the vector, and you are going to jump to there. Okay, you're going to jump to there. But this one, at this particular address, what we have is that you're going to have a long jump. Long jump, interrupt service routine, external 1, ISR, EXT1. Okay, this is just address. This is the address for your interrupt service routine. And where is the actual interrupt service routine? Right here. This is your actual interrupt service routine. And 200H, right here, right? I have a ISR, interrupt service routine, external 1, and I place this interrupt service routine at 200H. So this is our actual interrupt service routine. Okay? So you first jump to interrupt vector, and inside interrupt vector, you have a long jump. So therefore, you jump to there in actual interrupt service routine, and execute the interrupt service routine. And at the end of interrupt service routine, you always have a return I. So whenever you finish your interrupt service routine, then you have a return I. So when you see the return I, now we pop the program counter back, and then you come back where you left off, and then continue. Okay, this is the general process of how the interrupt service routine works. Okay? This is a little bit more complex program. Since we have 5 different interrupt sources, we have these much of interrupt vectors. Let's say you enable all of the 5 different interrupt sources. In that case, you need to have 5 different interrupt vectors. At 0003, in interrupt vector right here, we have long jump ISR external 0. Because this 0003 is the interrupt vector for external interrupt 0. And 000B, that's the address for interrupt vector for timer 0 interrupt. Okay, we have a 0013, 1B, 23. That is the address that I show you here, right? So these are the address for interrupt vector for particular interrupts. So we have 5 different interrupt, and each interrupt have the interrupt vector right here. 3, B, 13, 1B, 23. Okay, those are the known location. So if you want to use all of the different interrupts, then you have to have all of these, right? 3B, 13, 1B, 23. For each of these interrupt vector, now what you need to have is that you're going to have a long jump. And you're going to jump to actual service routine, interrupt service routine. So your actual interrupt service routine is somewhere else. For example, in this case, you have it here. So this is actual interrupt service routine for external interrupt 0. And this is the actual interrupt service routine for your timer 0 interrupt. Something like this. Okay? You don't have to have all these 5 interrupts. Okay? If you want, then maybe you want to enable only the timer 0 and external 0. If you want, then I can only enable 2 different interrupts. Or if you want, then you can enable all of them if you need them. Okay? So depending on how many interrupt sources you want to enable, you need to make sure that you have to have interrupt vector. And you have to have that the interrupt vector has a long jump to actual service routine, and your actual service routine can be in anywhere. Okay, you can place this particular picture is just an example. Like this is your program, right? This is your actual program. And this is just the example that you place your actual code to 100H. Maybe your program can be in 200H, 500H. Doesn't matter, right? Doesn't matter. Because whenever the microprocessor starts, it executes this line. And this one start basically is referring to this one. So you're going to jump to where you have anyway. So this actual address doesn't matter. Same here. You can place your interrupt service routine any place. This is just the example that I placed my interrupt service routine at 200H, but you can place this interrupt service routine at 1000H, 2000H, wherever you want. It's okay. As long as you have the right label here. Okay, this one basically is a label. So as long as you have the right label, and as long as you have the right instruction in the vector, interrupt vector, it's okay. You can put this one, the actual interrupt service routine, in anywhere. Okay, so this is the step how to make the interrupts work. First thing to do is that you need to decide if you need interrupts. Okay, if you need interrupt. Let's say what is a good example? You need to decide whether you want to enable the interrupt or not. Okay, in this case, let's think of an example. Like, let's say you're reading a book at home, and let's say your friend yesterday said that I'm going to call you tomorrow. So I know that my friend is calling me today, but he didn't say when. In that case, what do you need to do? If there is an interrupt, like a telephone rings, in that case, you don't have to watch the telephone, right? You can just do whatever you want. Like I'm reading a book, I'm doing homework, I can do whatever I want. Forget the telephone, I can do my work. And only when your telephone rings, then I go there and pick up. Now that's kind of interrupt, right? That's why we enable the interrupt. Now suppose that there's no interrupt. In other words, telephone does not ring. Maybe you put that in the mute mode or something. It does not ring. So in that case, what do you need to do? I know that my friend is calling me today, but telephone does not ring. Then what do you need? Maybe in that case, I have to go there and pick up the phone in every 10 minutes or so, right? Okay? I have to go and check every time. Every minute I have to go and check. But that's very bad, right? That's the case when you have no interrupt. So basically, that's the reason why we need to interrupt. The basic reason that we want to interrupt is that I want to do my own work. Okay? I want to do my own work. And then whenever some of the event occurs, in this case it's telephone ring, whenever the event occurs, then just let me know. Okay? Only then I'm going to go there and do something. Otherwise, I'm going to focus on my work. That's the main purpose of doing interrupt. Okay? So again, if there's no interrupt, then what do you need to do? Then you have to go there and check every time. Like this one. For example, right? Maybe another example. Let's say you are a manager. Okay? You are a manager at a team, and let's say there are maybe a couple of different guys working for you. You are a manager, right? And let's say your job is to assign some of the work to those guys. Okay, let's say I have three guys working for me. So I have this much of work to do, right? So what I do is that I'm going to give this amount of work to the first guy. And for the second guy, okay, you're going to do this work. I'm going to give him this much work. For the last guy, I also give him this much work. And once you give each of the guy work, some amount of work, then as a manager, what do you need to do? You want to check the status, right? You want to check. So there are two ways. One way is that maybe go there and ask him, okay, how things are going, you know, something like this, right? Every minute, go there and check. And in maybe 5 minutes later, go there and ask again. In that case, right, what's going to happen? Maybe they're going to leave, right? They're going to leave they're going to hate you as a manager. So what is the best way? Best way is to ask them, give me interrupt. Whenever you finish your work, give me interrupt. That's a better way, right? Only then I can focus on my work. Okay? I don't have to go there and check. Whenever they are finished, they come and tell me. That's interrupt. So always, pretty much, interrupt is more efficient. Okay, interrupt is more efficient. That's one of the reasons why we use interrupts. So first thing to decide is that what do you want to do as an interrupt? That's the first thing to do. And once you decide what to do with the interrupt, then you need to write up your interrupt service routine. Like, for example, this one, right? This is the interrupt service routine. What do you want to do within the interrupt service routine? So that's what you need to do. And then you have an interrupt service routine. Then we need to have interrupt vector. What was the interrupt vector? This one. Because your actual service routine is right here in some random place. So therefore, you need to make sure that you are going to do a long jump to your actual service routine. So this is the interrupt vector, right? So you have to make sure that you write interrupt vector. And also, in your program, you have to make sure that you're going to enable the interrupts. Because this is the condition that your interrupt occurs. So what is the condition? What was the condition for interrupt to occur? Remember these three conditions, okay? In order for interrupt to occur, we have to have three conditions. Actual interrupt event occurs, and also the interrupt flag for that particular interrupt is enabled, and global interrupt is enabled. Okay, we have three different conditions for interrupt to enable. Actually, I skipped this one, but there's another register called the IP, interrupt priority. This is another register. Okay? And this register have 5 different bits like this. And P means priority. And same way, X means external 0, timer 0, external 1, timer 1, and the serial port. Same order like this, right? Look at the 5 different bits here, and basically same order. And this particular bit is for setting the priority. So if you set this bit, for example, like here, right? If I make this bit to 1, that means I want to make my timer 0 as higher priority. If, right? So setting this 1 to make the higher priority, and setting 0 making the lower priority. Okay? So, but it's basically up to you. If you want, then you can make all 0, or making all 1, or only some of them making 1, or the others make 0. It's all up to you. So that's the last thing. You want to enable the interrupt bits and also setting the priority. And finally, you want to enable the global interrupt bit, the first bit in the interrupt enable register. Okay, once you do that, now then we can have interrupt. Any question on the interrupt? This interrupt is very important. We are going to cover some of this also in the next week. Question? No? Okay, then see you next week.